Here's some help with the Experiment 5 pre-lab. So the first question says, write the balanced chemical equation for the reaction between strontium and sulfur, and I have a picture of these below. Here is a video of that reaction happening. So the question says to write the balanced chemical equation for that reaction between strontium, which if you look on the periodic table has the symbol Sr and is a solid, and sulfur, which if you look on the periodic table has the symbol S and is also a solid. So the reaction between those two, we have to figure out how they combine. So to do that, we need to know whether the two elements will combine as an ionic compound or as a covalent compound. Ionic compounds are metals and nonmetals, and covalent compounds are two nonmetals. So there's a line, a sort of stepping stone on the right side of the periodic table. Here it's shown in black. If anything is to the left of that line, then it's a metal, and you can see that strontium is a metal. If anything is to the right of that line, then it's a nonmetal, and you can see that sulfur is a nonmetal. So, because strontium is a metal and sulfur is a nonmetal, the compound is going to be ionic. So to figure out how these two elements combine, we need to know their charges. So we can go to the periodic table, and we get the charge from the column that it's in. So strontium is in column 2A, so it's going to have a 2+ charge. And sulfur is in column 6A, so it's going to have a 2- charge. So those charges are the same, so you only need one of each element to balance the charges out. And so you just rewrite SRS, that's the product, and that happens to be a solid. And so that's the equation. We just need to make sure it's balanced. We have one strontium on the left, one strontium on the right, one sulfur on the left, one sulfur on the right, and so it is balanced. And that is the balanced equation for the reaction between strontium and sulfur. The second question says a 2.97 gram sample of iron combines with chlorine gas to form an iron chloride with a mass of 8.63 grams. And I have pictures of those compounds below. And here is a video of that reaction happening. So there are several parts to this question, and the first one is, what is the mass of chlorine added? Okay, so we know that we had 2.97 grams of iron, that we combined it with chlorine, and that we got 8.63 grams of iron chloride. So the mass of chlorine must be the mass of the iron chloride minus the mass of the iron, which is 5.66 grams of chlorine. And so that is the mass of chlorine added. The second part of the question asks, is the chlorine added to the iron present as chlorine molecules or chlorine atoms? So chlorine molecules are two chlorine atoms bonded together, which you can see here below. The diagram on the left shows the bond and the diagram on the right doesn't. But you can see how those are molecules because the two chlorine atoms, or if you think of them as Legos, are sticking together. And so they create something bigger, a molecule. So that's how chlorine exists when it's that green gas. And you have to rip the chlorine atoms apart before they combine and before they can combine with iron. And that's the reason why they heated the iron in the video. That heat was able to rip the chlorine molecules apart so that you just had atoms that could react with the iron. so they're present as molecules. The third part of the question asks, what is the mass percent of iron and chlorine in the final compound? So in general, a percent is a mass percent, is the mass of a part over the mass of a whole times 100. So we just need to put the masses of these different parts over the mass of the whole times 100 for each of them. So the mass percent of iron is going to be the mass of iron over the mass of the whole compound times 100. The mass of iron is 2.97 grams. They give us that in the problem. The mass of the whole, they also give us in the problem. That's 8.63 grams. So we take that, multiply it by 100. We get 0.344 times 100, and so 34.4% iron by mass. This compound is 34.4% iron by mass. So there we have the mass percent of iron. We also need to find the mass percent of chlorine. So the mass percent of chlorine will be the mass of chlorine over the mass of the whole compound times 100. We found the mass of chlorine in part A. That was 5.66 grams of chlorine. We know that the mass of the whole compound is 8.63 grams of iron chloride. They give us that in the problem. So we'll take that, multiply it by 100, and that'll give us 65.6% chlorine by mass. Part D of this question asks, what is the empirical formula of the iron chloride? So to explain this, first we have to know what an empirical formula is. I think the more intuitive thing to understand is what a molecular formula is. Let's say we had something like C6H12O6. That's the molecular formula for a molecule called glucose. It's blood sugar. So that tells you the exact number and types of atoms in a molecule. Here I have a model of glucose on the right, and each of the gray atoms is carbon, each of the white balls is a hydrogen atom, and each of the red balls is an oxygen atom. And you can see that it has 6 gray balls, 6 carbons, 12 white ones, 12 hydrogens, and 6 red ones, which is 6 oxygens. And so the molecular formula tells you exactly the number of atoms in the molecule, the exact type and number of each atom in a molecule. If you were to take each of those atoms and divide them by the lowest common multiple, in this case 6, so that you reduce the numbers just to get the ratio, then you'd get the empirical formula. So while the molecular formula gives you the exact number of atoms in a molecule, the empirical formula just gives you the simplified ratio of atoms to each other in the molecule. Now, so for example, you'd have 1 carbon atom for every 2 hydrogen atoms. Now, moles are just a number of atoms, and so the ratio of atoms to each other is going to be the same as the ratio of moles to each other. So we could say that for every 1 mole of carbon, we'll have 2 moles of hydrogen. So we can find the empirical formula by finding the ratio of moles of each element to each other in a compound. So to find the empirical formula, first we're going to have to find the number of moles of each element in the compound. Then we're going to divide the number of moles of each element by the smallest amount of moles, and we're going to use that number as the subscript for each element. So first, to get the moles of each element of the compound, we know we have 2.97 grams of iron, and I'd like to convert that to moles. So I'm going to write a multiplication sign and a fraction bar. The units that I start with on top, in this case grams of iron, is going to go on the bottom because I want it to cancel out. And I'm going to fill that in using the conversion factor that I get from the periodic table. The number underneath each symbol in the periodic table tells you how many grams are in 1 mole of that element. So in this case, 1 mole of iron has 55.85 grams of iron. And you can see how I wrote it in the equation. So in that fraction, I'm going to put the number that goes next to the grams of iron in that conversion factor, 55.85. And going over the fraction bar is like going across the equal sign. So on top, I'm going to write 1 mole of iron. Grams of iron cancels, and I'm going to get 0.0532 moles of iron. I'm going to try to do the same thing with chlorine. We had 5.66 grams of chlorine. We figured this out in part A. Do a multiplication sign, a fraction bar, and the units that you start with on top go on the bottom because you want them to cancel out. I'm going to fill that fraction in with a conversion factor that I get from the periodic table. Because the number below the symbol for chlorine is 35.45, I'm going to say 1 mole of chlorine equals 35.45 grams of chlorine. I put the number next to grams of chlorine in the fraction. Going over the fraction bar is like going across the equal sign, so I put 1 mole of chlorine on top. Grams of chlorine cancels, and I get 0.160 moles of chlorine. So I found the moles of each element in the compound. Now I'm going to divide each of those moles by the smallest amount of moles. So in this case, the smallest amount of moles is 0.0532. So I'm going to divide both of those amounts of moles by that, the smaller amount of moles. That turns the moles of iron to 1 and the moles of chlorine to 3. Finally, I'm going to use those numbers as the subscripts for each element in the compound. So for iron, it's going to have a subscript of 1. Just by writing the iron, I have the 1, so I don't have to write the 1. And the subscript for chlorine is going to be 3. So the empirical formula for iron chloride is FeCl3. Third question says, the following data was obtained from a student's experiment when zinc was heated with sulfur. Complete the data. Show your calculations at the bottom of the page. And they give you the first data points for the mass of a crucible and lid, the mass of zinc crucible and lid, and the mass of crucible, lid, and final compound after the reaction. So first let's just see what this reaction's about. We have zinc reacting with sulfur. Here's a video of that. Okay, so the first thing we might try to find, our goal here is to get the moles of each element, both the zinc and the sulfur, because we want to find the empirical formula, which is the ratio of the moles of each element to each other. So to find that, first we need the mass of each element. So let's try to find the mass of zinc. Here they give us the mass of zinc, the zinc crucible and the lid. If I take that and I subtract the mass of just the crucible and the lid, you can see that the crucible and the lid will cancel out, and I'll just have the mass of zinc. So in this case, zinc is going to be 1.74 grams. And I write that in that box in the table. Next, I'm going to try to find the mass of sulfur. Now I know that the only things that reacted here are zinc and sulfur to give me the final compound. So I can sort of rearrange things, subtract zinc from both sides, and I know that sulfur is going to have to be the final compound, the mass of the final compound minus the mass of zinc. So I have the mass of zinc, we just found that, and we just need to find the mass of the final compound. So let's take a small detour to do that. So to find the mass of the final compound, we have the mass of the crucible, the lid, and the final compound. If I subtract the crucible and the lid, you can see that those will cancel out, and I'll just have the mass of the final compound as 2.59 grams. So now we have the mass of zinc and the mass of the final compound. So the mass of sulfur is going to be mass of the final compound, 2.59 grams, minus the mass of zinc, which is 1.74 grams, and that's going to be 0.85 grams. And I'll just write that in the box on the table. Okay, now that we have the grams, let's convert them each to moles. So let's convert those grams of sulfur to moles of sulfur. So we need a conversion factor that relates grams of sulfur to moles of sulfur. We get that from the periodic table. So there are 32 grams of sulfur for every 1 mole of sulfur. So we write the number, write a multiplication sign and a fraction bar. The units on top go on the bottom because we want them to cancel. And then we fill that fraction in with the conversion factor. So 32 goes next to grams of sulfur. 1 mole of sulfur goes on top. Grams of sulfur cancels out, and we're left with 0.027 moles of sulfur. And you just write that in the table. Let's try to do the same thing with zinc, try to find the moles of zinc. So we need a conversion factor that relates grams of zinc to moles of zinc. And we use the periodic table for that. Using the periodic table, you've got 65 grams of zinc for every 1 mole of zinc. we have here 1.74 grams of zinc, so you write a multiplication sign, fraction bar, and the units on top go on the bottom because you want them to cancel out. And then you just fill that fraction in with the conversion factor. So 65 goes next to grams, and on top is 1 mole of zinc. Grams of zinc cancels out, and you're left with a certain number of moles of zinc. And just write that in the table. Okay, now the time for the empirical formula. So we have this many moles of each element. We're going to divide each of those moles by the lower number. In this case, they're the same, so we're going to divide them both by 0.027. That gives me 1 for each. And I'm going to use that as the subscript for each element in the final compound. So zinc with a subscript of 1 and sulfur with a subscript of 1. But because just by writing the elements you know you have one of them, you can get rid of those subscripts. So I'm going to write that into the table, and that's my answer for this problem.